This is part 2 of the lecture on atmospheric water. It's about measuring precipitation and estimating evaporation. Measuring precipitation. One may simply think of rainfall depth as the real depth of a layer of water on a flat impermeable surface after rainfall. A low-budget way to make a simple collector-type non-recording rain gauge for measuring the rainfall depth is to buy a plastic bottle in a shop, drink or dispose of the bottle's contents, cut the top from the bottle at about 2/3 of the height of the bottle, turn the top around and attach the turned over top to the lower 2/3 of the bottle, as shown in this figure. The top of the bottle acts as an orifice, an opening, that catches rainfall, and the lower part as a cylindrical container where rainfall is stored. Finally, dig a small hole in the ground and tightly fit the bottom of this rain gauge into the hole. To determine the rainfall depth, proceed as follows. Determine the radius of the orifice in centimeters. The radius is half the diameter. Determine the surface area of catch of the orifice in squared centimeters. This equals pi times the radius of the orifice squared, with pi being 3.141, etc. Empty the bottle after a rainfall event or at fixed time intervals, and measure the volume of rainfall in cubic centimeters, which, by the way, is the same as milliliters. Simply divide the volume of rainfall in cubic centimeters by the surface of catch of the orifice in squared centimeters, and multiply this result by 10 to obtain the rainfall depth in millimeters. There are three main types of recording rain gauges, registrerende regenmeters, for measuring precipitation at a point location. The weighing rain gauge to the left, the float and siphon rain gauge in the middle, and the tipping bucket rain gauge, het kantelbak systeem. In a weighing rain gauge, to the left here, the mass of the water in the gauge is continuously measured and registered. Since 1 liter of water has a mass of 1 kilogram, any difference in mass can easily be converted to a difference in rainfall volume and thus rainfall depth. In a float and siphon rain gauge, the depth of the water in the cylindrical water collector is continuously measured and registered using a float resting on the water. A siphon empties the water collector once the water has reached its maximum height. And this corresponds to the position of the bending end of the siphon. In this way, rainfall depths and intensities can be determined. In a tipping bucket rain gauge, the bucket tips over each time a certain volume of rain has fallen, usually corresponding to a 0.2 millimeter rainfall depth. By registering the timing of the tips, the average rainfall intensity each time the bucket tips, as well as rainfall depths over longer periods of time, can be determined. It is probably useful to mention a number of the problems that one can encounter when measuring precipitation. When placing a rain gauge in the field, one should take care to ensure that the rain gauge is well exposed. For instance, that the distance from a high object is sufficiently far as not to be measuring in the high object's rain shadow. The rain gauge is an obstacle to wind, causing turbulence, and as a consequence, raindrops may be blown out of the orifice, leading to an underestimation of the rainfall depth. The higher the orifice, the larger the wind speed, plus the smaller the water droplets, the more pronounced the undercatch of the rain gauge will be. To prevent underestimation of the rainfall depth, it is best to measure rainfall depth in a ground level rain gauge as shown here, where the top of the rain gauge is placed at ground level at the center of a grid and brush network that prevents the splashing of raindrops from the ground into the gauge's orifice. Another reason may be that a hydrologist usually wants to know the rainfall depth entering the soil rather than the rainfall depth at some standard height above the ground. In many hydrological or environmental studies, the interest lies with aerial precipitation, rather than precipitation at a single point in the landscape. This involves the design of a network of rain gauges. If the area under study is flat, the rain gauges can be distributed evenly over the area. Usually, not many rain gauges are needed. For estimating the aerial precipitation, the arithmetic mean precipitation depth, or the use of Thiessen polygons may suffice. Here we have an area under study for which we want to know the aerial precipitation, and we have three rain gauges, A, B, and C, with C lying just outside of our area under study. Thiessen polygons are built up by drawing midlines, perpendicular bisectors, between the rain gauges on a map. Perpendicular bisectors of any three rain gauges meet in one point. To each area that surrounds a rain gauge, the value of the precipitation depth measured in the rain gauge is assigned. So for rain gauge A, it's this area. For rain gauge B, this is the assigned area. And watch out for rain gauge C, which lies just outside our area under study. This is the assigned area. Multiplying the precipitation depth by its representative area, then summing these products for all rain gauges, and then dividing by the total area under study gives us a weighted average of the precipitation depth over the area. This method is more accurate than calculating the arithmetic mean, but it's rather inflexible, since missing data from any one of the gauges calls for a new network to be constructed. Also, the Thiessen polygons do not cope well with orographic effects in precipitation. When precipitation is spatially highly variable, such as in mountainous areas, or if a high accuracy of estimate is required, more rain gauges are needed and their positioning in the landscape becomes more important. When using the isohyatal method, lines with the same precipitation depth, so-called isohyates, are constructed. For instance, here we have an area under study for which I want to know the aerial precipitation. I have a number of rain gauges. Listed are the precipitation depths for these rain gauges, and the isohyates are constructed. Here we have an isohyate of 10 millimeters, and here we have part of the isohyate of 20 millimeters. So in this area, we have on average 15 millimeter. I can multiply the 50 millimeter by its area, do so for all the other areas, and then summate these numbers and then divide by the total area under study. This gives me a pretty good weighted average of my precipitation depth, my aerial precipitation. Although the drawing of isohyates is slightly arbitrary and may involve some experience, the topography and also knowledge of the storm pattern can be well accounted for when using this method. Nowadays, good use is made of radar in estimating aerial precipitation depths. Radar does not directly measure precipitation. Radar is an acronym for radio detection and ranging. With radar, an empirical relation between the radar reflectivity and rainfall is used. More reflectivity indicates a larger likelihood of precipitation. Radar can produce estimates of precipitation for time intervals as small as 5 minutes and for areas ranging from 4 to 138,000 square kilometers. As an example, this figure shows daily precipitation values estimated from radar observations for an area of approximately 83,000 square kilometers, including the Netherlands. Daily precipitation values for the Netherlands on the 4th of April 2004 are shown to the left, and for 1 May 2004 to the right. These are estimated from observations by 2 radar stations. The 4 April event shows low precipitation values over a large area, whilst the 1 May event shows high precipitation values over a small area. The latter is most likely to be convective precipitation. Useful meteorological data, for instance, for estimating the evaporation, as we will see slightly later on, can be obtained after installing a meteorological station. That's a lot of hard work. As you can see here, this is our meteorological station in our fieldwork area in the Hautes-Alpes in France. Air pressure is measured, precipitation in a tipping bucket rain gauge, wind speed, wind direction, solar radiation, relative humidity and temperature. And students, you can find the data of this station on Blackboard. This is a nice picture showing you the variation of vapor pressure, relative humidity and air temperature during a day. On the vertical axis we have the vapor pressure in hectopascal. We have the relative humidity. The relative humidity is defined as your actual vapor pressure divided by your saturation vapor pressure. The saturation vapor pressure is a function of temperature, as we already saw by means of the Clausius-Clapeyron curve. And here on this vertical axis we have temperature. So the temperature changes over the day. In the morning it's cold, and then during the day it gets warmer, and then in the evening it cools down again. The actual vapor pressure in this example stays the same, but you see that because of the changing temperature, your saturation vapor pressure values change, and because of this, that your relative humidity changes. So your relative humidity is large in the morning because temperatures are low, and the relative humidity is lower in the afternoon because your temperature then is higher. This picture shows us part of a saturation vapor pressure table or Clausius-Clapeyron relation. The full table is given on Blackboard, and you will need that table in order to be able to make one of the Chapter 2 additional exercises. In this vertical column we have the temperature in degrees Celsius, and in this vertical column we have the saturation vapor pressure in hectopascal at these temperatures. If you know the temperature and the relative humidity of the air, you can figure out what your actual vapor pressure is at that temperature, and you can also figure out what the dew point temperature or frost point temperature is. There are 3 key types of evaporation. Precipitation that is intercepted by vegetation may evaporate back into the atmosphere, interception evaporation. Water evaporates from a wet soil surface, soil evaporation, or water evaporates through plant stomata, thus from within the plant, transpiration. On a global scale, about 57% of all precipitation on land evaporates. 112% of the precipitation that falls on the oceans evaporates. This percentage is larger than 100 because rivers deliver additional water to the oceans. Also, in warm, dry climates, up to 96% of the yearly precipitation may evaporate. Evaporation, thus, constitutes an important part of the hydrological cycle. A twofold distinction of evaporation at the land surface can be made. Potential evaporation is the maximum evaporation rate in millimeter per day when the moisture content of the soil and vegetation conditions do not limit evaporation. In other words, under unstressed conditions. Actual evaporation is the evaporation rate in millimeter per day under existing atmospheric soil and vegetation conditions. The atmosphere may be humid, the soil may be dry, and/or plant stomata may be closed. These are all circumstances that limit evaporation. The actual evaporation is therefore always less than or equal to the potential evaporation. The reference crop evaporation is the potential evaporation in millimeter per day of an idealized grass crop that serves as a reference value for determining the potential evaporation of other crops. A low-budget and direct way to obtain some measure of the evaporation rate on days with no precipitation is to use a pan filled with water and to measure the height of the water in the pan for 2 consecutive days at exactly the same time. The difference in height in millimeter divided by the time interval in day yields the pan evaporation in millimeter per day. The open water evaporation is the rate of liquid water transformation to vapor from open water in millimeter per day. The pan evaporation in millimeter per day will generally be higher than the open water evaporation in millimeter per day from a lake nearby. One of the reasons for this is that the small size of the pan ensures a warming effect of the sides of the pan by solar radiation. This will significantly enlarge the evaporation output from the pan because of the warming up of the water inside the pan by the pan itself. Thus, to obtain open water evaporation rates from pan evaporation data, the pan evaporation values need to be multiplied by a pan coefficient, a fractional value larger than 0 and smaller than 1 that depends on the type of pan used and the time of use, the season. Here we have a photo of an evaporation pan, the US Class A evaporation pan. Other well-known evaporation pans are the Colorado sunken pan, which is a square pan sunk into the ground, or the US Geological Survey floating pan, which is a pan that floats on the water. P on an annual basis for these evaporation pans is approximately 0.8. This picture shows us the rate of evaporation in millimeter per day on the vertical axis for a high relative humidity of the air above the water as opposed to a low relative humidity of the air above the water as a function of the size of the evaporating surface, pans and lakes, open water evaporation. When the weather is warm and the relative humidity of the air is low, the difference between pan evaporation and open water evaporation will be larger than when the weather is cold and the relative humidity of the air is high. Thus, pan coefficients for the same type of pan are usually smaller, that is, a larger correction is needed in summer than in winter. A good way to obtain values of actual or potential evaporation is by installing a lisimeter. A lisimeter, as shown in this picture, is a device made of steel, concrete, or synthetic material dug into the terrain, in which a volume of soil, usually with vegetation, is isolated hydrologically, preventing leakage from the device. The position of the water table in the lysimeter is monitored and can be regulated by pumping measured amounts of water in or out. In a weighing lysimeter, the change in water storage is determined by the difference in mass of the lysimeter. The evaporation is estimated from the water balance. The diameter of a lysimeter typically varies from 0.5 to 2 meters, with larger devices having surface areas of the order of 35 times 25 square meters. Lysimeters are difficult and expensive to install, but are most useful in experimental research for obtaining empirical equations to estimate evaporation from meteorological variables. In the Netherlands, 4 lysimeters with a long track record since the late 1930s are located in the dunes nearby the township of Castricum. When we rank the evaporation types that we just discussed, going from high to lower millimeter per day values, this is the general ranking that we would obtain. Pan evaporation will generally be higher than open water evaporation, as just discussed, which in turn will be higher than the reference crop evaporation. The reference crop evaporation is the potential evaporation of an idealized grass crop, and this reference crop evaporation serves as a reference value for determining the potential evaporation of other crops. So this potential evaporation usually is smaller. Potential evaporation is the maximum evaporation rate when moisture content of the soil and vegetation conditions do not limit evaporation, and the actual evaporation is the evaporation rate under existing atmospheric soil and vegetation conditions. The actual evaporation is therefore always less than or equal to the potential evaporation. Due to the difficulties involved in measuring evaporation directly, it is generally estimated from meteorological data. The evaporation rate is controlled by the energy needed to diffuse water vapor into the atmosphere, the Earth's surface energy balance, and the atmospheric demand for water vapor. The Penman-Monteith equation is shown here, named after the work of the British physicists Penman in 1948 and Monteith in 1973, is a physically based method for estimating the actual evaporation EA, or under unstressed conditions the potential evaporation EP, based on both the energy balance and atmospheric demand. The heat transfer into a soil, rock, or water body is relatively small and can often be neglected. If we set this to 0 and insert values for the constants and near constants into the Penman-Monteith equation, this is what we get as an equation. Actual evaporation in millimeter per day. Rn is the net radiation at the Earth's surface in megajoule per square meter and per day. Es minus Ea is the saturation deficit in kilopascal, and we'll discuss this in a minute. Delta is the gradient of the saturation vapor pressure curve, or the Clausius-Clapeyron relation, in kilopascal per degree Celsius. It's basically temperature dependent, and Rs and Ra are resistances. Ra is the aerodynamic resistance. It is the resistance encountered by water vapor in diffusing into the air from a vegetation surface. Thus, it is the resistance against interception evaporation. It is reciprocal to the roughness of the Earth's surface and the wind speed near the surface. Both a rougher surface and more wind cause more turbulent mixing of the air and thus a smaller resistance to evaporation. Rs is the surface resistance. It is a physiological resistance imposed by vegetation stomata on the movement of water vapor by transpiration. It varies with water availability, the soil moisture content. Ra and Rs are resistances. They are typically expressed in seconds per meter, the reciprocal of meters per second. The Earth's surface energy balance. There's radiation from the sun. Part of the radiation that reaches the Earth's surface is reflected. Alpha is the albedo, or reflection coefficient. It's the fraction of incoming radiation that is reflected. Part of the incoming radiation is absorbed. Sn is the absorbed shortwave radiation at the Earth's surface. Rn is the net radiation at the Earth's surface and can be determined as the difference between the net incoming shortwave radiation, that is absorbed, Sn, and the net outgoing radiation at the Earth's surface, Ln. These radiation values are in megajoule per square meter and per day. The incoming radiation is shortwave because the sun has a high temperature. The outgoing radiation is long wave because the Earth has a low temperature. This net radiation energy at the surface, Rn, is used for warming the soil below the surface by soil heat transfer, G, warming the air by sensible heat transfer from the Earth's surface, H, voelbaar warmtetransport, and or latent heat transfer, which is evaporation from the Earth's surface, lambda Ia, latente warmtestroom, damping. G, H, and lambda Ia are all expressed in megajoule per square meter and per day, and are assigned a positive value when directed away from the surface. Besides the net radiation Rn as a source of energy, the atmospheric demand for water vapor also plays an important role in evaporation. This is shown by Es minus Ea in the Penman-Monteith equation. Es is the saturation vapor pressure at the evaporating surface in kilopascal, and Ea is the actual vapor pressure of the air above the evaporating surface in kilopascal. Es and Ea are estimated for the same air temperature. The difference between Es and Ea is called the saturation deficit, het verzadigingstekort in kilopascal. The larger the saturation deficit, the higher the evaporation rate will be. This slide shows the online resource center or companion website of my book. As an interactive spreadsheet, it contains a worked-out example of the Penman-Monteith evaporation, comparing the evaporation from a forest, grassland, and open water. The spreadsheet allows you to insert input values on meteorological data, such as air temperature, relative humidity, sun shortwave radiation, number of bright sunshine hours per day, and the total day length, and land use data, the albedo, the aerodynamic resistance, and the surface resistance for forest, grassland, and open water. This shows you the spreadsheet lower down. Here we have the output data on evaporation in millimeter per day for forest, grassland, and open water. The lower evaporation rate for forest than grassland is due to the high value of the surface resistance of the forest, and the high value of the open water evaporation is due to the low albedo value, so a low reflection of solar radiation, and of course the absence of a surface resistance. Allen and co-workers recommend the FAO Penman-Monteith equation as the sole standard method for computation of the reference crop evaporation ERC in millimeter per day. This equation is the Penman-Monteith equation for a grass crop height of 0.12 meter, a standardized height for wind speed, temperature and humidity measurements at 2 meter above ground level, an albedo of 0.23, an aerodynamic resistance in seconds per meter of 208 divided by U2, where U2 is the wind speed in meters per second at 2 meter and the surface resistance of 69 seconds per meter. Gamma here is the psychrometric constant and T is the air temperature in degrees Celsius. In order to estimate the potential evaporation of a particular crop, it is common practice to calculate the above-defined reference crop evaporation and to multiply this by the crop coefficient, Kc, of the particular crop, as determined from research, for instance, by using a lysimeter. The value of Kc changes with the growth stage of the crop. It was my pleasure to lecture you on atmospheric water. For the tutorial, we have the Chapter 2 additional exercises. Also, we have the online resource center multiple choice questions of Chapter 2. Next time, we'll be dealing with groundwater, and we'll start off with Bernoulli's law and Darcy's law.